Lars Kasper giving the next presentation, and the title of the talk is PhysIO, Unique and TAPAStry of Tools, Open Source Development at MRI Methods Application Interface, and he's actually currently based at ETH Switzerland, if I'm not wrong. Sorry, maybe I've made a mistake. Correct me if I am.
It's a bit complicated, but it's part of the theme. Yeah, thank you so much, Rita, and thank you to the organizers of MRI Together for inviting me. Thank you for being able to talk about PhysIO, Unique, and the TAPAStry of Tools, open source development at the MRI Methods and Application Interface. So yes, it has been developed originally in Zurich. A lot of the stuff I'm showing today, but I'm now in Toronto. So what is the MRI Methods Application Interface, and why is it that open source development is crucial there? I would argue that application is the final frontier for most of us here at MRI Together. So we all realize that MRI is complex with hardware, engineering, pulse programming, image reconstruction, and then processing the images and analyzing them and finally coming to clinical application. And we all try to make this workflow practically useful. And the details may vary. I've outlined a bit what I'm doing below. So my background is in brain MRI, and if I localize my expertise, I have some expertise with pulse programming and echoplanar and spiral imaging. Then did a lot of image reconstruction, parallel imaging, and DNOT corrections. And then also got involved into functional and diffusion MRI, and especially the processing pipelines there. So, but MRI, the final frontier of application, is also a moving target. So I would say that it depends on the training and the research interest, and also the current status of a project. So while some of my colleagues say the real methodological work starts after you've done the processing and they develop new methods of connectivity, that's kind of where my work ends. So basically, it's inherent to MRI as a complex methodology that it's transdisciplinary, and we are necessarily non-expert in most parts of a project. That also means we're working with many experts from other domains. And MRI research software, for that reason, has to be robust and accessible for domain novices who are otherwise experts, right? So it has to be transparent in its functionality to build trust, because researchers are naturally critical thinkers. And they are independent, so research software also has to be more flexible. So being at the frontier, no one size fits all. So we need expert parameters and custom extensions for the software as we develop. And I would say open source development fits this bill very well, because it's a commitment to accessibility and transparency, and also quality, because basically a lot of people can contribute and provide feedback. My road into open source development started with TAPAS, which is the abbreviation for Translational Algorithms for Psychiatry Advanced Science, which is a software package that has computational psychiatry as application and was developed in Zurich at the Translational Modeling Unit, led by Clark and Stefan. And it's licensed as an open source tool with GPL. That's basically because we work closely with STM, and has been downloaded about 6,000 times since 2017, which is probably an underestimation, because for a long time we didn't count how many repositories were cloned, and it's used annually, for example, in education in the computational psychiatry course in Zurich. So the TAPAS development model looks like that. We have many different phases throughout a computational psychiatry project, from the design phase, conducting the acquisition, checking the data quality, pre-processing, up to the inference level with very complex statistical tools, and then finally the clinical application. We want to diagnose or prognose, provide prognosis about patients' outcomes. And every project uses different parts of these tools, so you mix and match depending on what kind of application within computational psychiatry you have in mind. That also means we have different lead developers. All of them at one point were based at the TNU, and we agree on having joint releases for all the tools as this TAPAS software package, about 2 times a year, and regular developer meetings 1 to 2 times a month. Our philosophy is to always have this common goal of applying the software for computational psychiatry in mind, but on the other hand, have a very tool-specific responsibility of the developer. So there's lead maintenance for each of the tools that you see here with all these abbreviations. And we agreed on one development platform, which used to be MATLAB, also for historical reasons with STM. But we are now transitioning to Julia. So with Peter Carlos, so for the same reasons, basically. And we agreed on having joint coding styles, naming conventions, tests, and guaranteed interfaces between the tools, because we want to really for people to be able to use these tools and be familiar with how they're working. And if I wanted to describe our development model, so you've probably heard of this move fast and break things. That's not our model. It's rather move last and curate things. So we want to be sure that things work over decades, basically, and long term. And the rest of the talk, I will talk about the two toolboxes where I'm one of the lead developers, which are PhysIO and UniQ, which are mostly used in the design stage and the checking, correcting, and pre-processing of the data. So the PhysIO toolbox for physiological noise correction in fMRI was developed because physiological noise is one of the main issues in fMRI, functional MRI, because you have signal fluctuations from physiological sources like the heart or lung that have no localized neuronal origin, and they basically create a sea of noise within you, try to find the little drops of fMRI activation. And there are some pulsatile, like the heartbeat and the respiration create some displacement and flow of liquid and tissue in the brain. And there's also more global tissue star-like changes that are subsumed under the cardiac and respiratory response and have to do with changes in flow and CO2 levels within the brain. And after you correct for motion in any fMRI time series, this accounts for the majority of signal variance in the brain. So you have an example here, is activation map, for example, the cardiac pulsatility. If you correct for that, it reduces 70% of the remaining variance in these regions that are highlighted in the top panel. And PhysIO tries to model these physiological noise contributions by using peripheral recordings like ECG and respiration cells with established models for the noise modeling. So first officially released in 2013 and has been picked up in the community, and we still actively develop it. The features of PhysIO was that when we developed it, we tried to address three major challenges. First of all, we needed a flexible region for different data formats, because each vendor basically has their own log file format for this physiological data. And you can see a list of the current supported data formats. And for all of them, we include example data and scripts. We also support BIDS as one of the community standards. And this is how you can get started. You just initialize and download the example data, and then you can try out these for your own. Second, the data quality of peripheral recordings varies considerably in practice, and that makes robust pre-processing essential. So it's not enough to just read in this data. And we have tested PhysIO on a lot of different systems and subject populations, for example, ADHD or ultra-high sleep strength. And thanks to our focus on signal processing, we are able basically to support a lot of these more complicated data sets. For example, for the cardiac data, we have iterative peak detection developed by Stefan Bollmann, which allows us also very noisy data to retrieve the R peaks of an ECG. And for the respiratory data, we developed a new volume estimation for the respiratory volume by separating the respiratory volume trace into an instantaneous breathing volume, breathing rate. That was worked by Tim Harrison. And we've shown that, for example, in very common but atypical breathing events like yawning, this is a much better estimate than the classical peak-based estimation of respiratory volume. And the third feature of PhysIO that we found important was the assessment and automation to check whether the resulting noise models are actually working. and how effective they are. So basically, after providing a regressor matrix text file, we utilize a generated linear model within SPM to report the denoising performance and can create maps of the explained variance or the TSNR, the temporal signal to noise gain, by incorporating these models. If you want to get started with PhysIO, the easiest way is to use MATLAB and then just follow the README. You can download and initialize it. Let's show you a little video. Initialize TAPAS, and you see that basically everything is done automatically in these examples, from reading in the data to all the way to creating the regressors, and then we have additional tools to also then use these regressor matrices for the model assessment. Recently, we've also made PhysIO, so we basically have a GUI interface so that you can change these parameters, you can work in the script as well. And recently, we have also made it available as a standalone version within NeuroDesk, which is basically an online containerized solution. So you don't need MATLAB anymore here, and can basically just try it out in a browser. If you want to get involved in PhysIO, you can contribute on GitHub, or you can actually join the Brain Hack. We have a project coming up there, I think, mid of December, 14th or 15th of December. Now to switch gears, the second toolbox that I want to introduce is the UniQ toolbox as part of TAPAS for unified neuroimaging quality control, where we looked at a typical use case if you're an MR physicist or basically a processing focused researcher, where you have developed a really cool MR method, but how do you show that it's of any use for the fMRI community and being robust basically in a pipeline for an actual patient study that might run a few years? And the idea is you want to show that it really increases sensitivity, so that the uncorrelated noise is reduced, you boost the signal to noise ratio, but also you want to make sure that specificity is not compromised. So what do we actually fit with our model, and what happens basically with the distribution of the brain? You see on the right here multiple use cases where we can use UniQ in that context. So we can use it to detect MR artifacts by visualization, compute sensitivity with signal to noise maps, combine it with SPM to compute reference activation for very simple tasks where you basically have a ground truth, and then also compute our analysis to see that we really optimize for the regions that we are interested in for fMRI. And because these are kind of very related but different tools, UniQ is more like a meta toolbox for quality control, which allows fast prototyping and reproducibility to benchmark these fMRI methods. And again, I've just developed this last year, was published as an ISMM abstract, and the paper is in preparation for a long time, which also refers to what I want to talk about in the end. And it's also part of TAPAS at the moment, since 2020. So the design principles of UniQ are, again, flexibility. We want to be able to handle images with arbitrary dimensions because that's what happens if you prototype. And we want to be operationally flexible, so provide basic building blocks and build complex pipelines as they're used in functional MRI. We want to be reproducible. Everything should be scriptable, but also human readable. So we adapted for an object-oriented implementation that is also tightly integrated with MATLAB and SPM so that we don't have to reinvent the wheel for established techniques. And finally, we want accessibility. So we want to use a rather native notation. So using objects like variables. So if you want to compute the SNR, it just should be the mean of the image time series divided by the standard deviation, like here on the right, whereas X is now here mass dimensional. And of course, if you want to make it accessible, you need a very good documentation. Use the MATLAB help browser. Yeah, let's just have a look how that works in practice. Okay, so basically we can load an image into our MATLAB command window and just plot it and get an overview of that. But then you can customize this plot to your needs. For example, you're interested in certain slices, but you want to see all the images for that slice. And then you want to put the SNR in that image time series. And then look what happens when you perform any specific processing steps, in this case, realignment. So it's called SDM. So we can now compare our realigned image RI to our raw image I and have a look how the SNR changes. So you can see basically mostly everywhere in the brain you get a significant SNR change. If you want to look what the filter is doing and this filter was not implemented, UniQ is also very extendable. You can just perform any unary operation that is supported in MATLAB as a one-dimensional function in multiple dimensions. And then again, look at how this filter improves our SNR. You can look at the Fourier transform. So that's what MR physicists do. And then what is important, especially for fMRI, is to look at the performance in the visual region. So you compute region of interest mask, automate it here, and then you can extract the data in that mask and look at the statistics, for example, as a histogram. And you see basically here we have a peak at about a temporal SNR of 50. And you want to know basically where actually was my mask. And you can see actually the mask is not so tight within the gray matter of the brain. So you can have a look in the documentation how to improve that mask and then create a better, more fitting mask. And you see basically this interactivity in the prototyping is really important, right? You go back from visualization to processing to visualization. And the same is true if you, for example, look for artifacts in image time series. That's one of the core things we wanted to make available with PhysIO. Yeah, sorry, with UniQ. All right, so this was a short overview of what you can do with UniQ for developing your fMRI pipeline. And now I wanted to quickly reflect on our development model. So the advantages, I would say, are that it allows for very robust and mature software releases. So since all of us started at one point at the TNU, there's a sense of agency, ownership for the toolboxes, even if you go, for example, from Zurich to Toronto, that can be sustainable over years and decades. And there's distribution for publications, for example, in academic TV, right? Because we still live in an era where individual contributions are evaluated if you want to progress in academic career. And what I find also is that it offers deep solutions. So every developer who's in there has a thorough understanding of the philosophy and goals of what we're doing in TAPAS. And when you give this example, instead of asking, how can I realign multi-echo fMRI data, Saskia and I developed rather a general solution for how can I apply any geometric transformation to an n-dimensional data set based on its estimation of k-dimensional subsets, right? So these are the things you typically only can do if you have a deep understanding of what the tool is doing. The challenges of this development are also considerable. I mean, we require steady base funding. So each toolbox, my time commitment is 10 to 20% of my research time. And there's a certain lack of academic software-specific grants. There's not a lot where you can basically just say, I want to develop software that then helps other projects, because most academic funding is project focused. There's a very slow release cycle, 1 to 2 times a year. And the integration of external contributions is difficult, both because of the communication, but also because there's a steep learning curve because we need deep solutions. Yeah, with this, I would like to thank you for it and acknowledge all the contributors. So these are the ones that have made the dive into this and use this opportunity as a steep learning curve. And I would also, if you're interested in the future of coding, I would also point out that we are contributing and participating in the Brain Hack this year. So if you want to get involved, have a look at the Brain Hack website. Thank you.